One more thing I want to link with the stoichiometry of a chemical reaction has to do with basically how much energy that reaction will release or how much energy that reaction will require. So those two types of reactions, a reaction that will require energy or a reaction that will release energy, are balled up in one of the things we need to tackle first. So endo actually means in, thermic means heat. So basically, reactions that you need to take heat and add heat, put heat in order for the reaction to occur, that's what we call endothermic reactions. And in that case, we can kind of think of the heat energy as a reactant. Okay. And I have an energy diagram to kind of show you here in a minute. If this is kind of this could be time along the x-axis and energy along the y-axis. In this case, actually, this says the final state products are at a higher energy than the lower state. So this would be our reactants, energy in, and this is our products. I guess it probably goes like, I don't know, it probably goes like that. Okay, this is our products. Okay, so this is like the energy diagram of an endothermic reaction. This actually introduces something that I definitely talk about in my other chemistry class. The letter H stands for enthalpy. H is enthalpy, and actually in many cases at constant pressure, enthalpy is a measure of the thermal energy of an object. So enthalpies can be positive or negative. So when it says delta H, the change, by the way, I think we've run into this deltas before. This triangle means change in. Delta means change in. So basic. Okay, so endothermic and exothermic. So exo, the way I think of is exit, and thermic means heat. So this is heat exiting, okay? So your reaction will release energy. And here in a minute, you're going to see that we can, if it's releasing energy, we're going to actually put energy on the product side. And with regard to an energy diagram, you're going to see, like if this is my energy diagram, and time goes from left to right, and however high it is along the y-axis, that means how much energy it has. In this case, it's going to start, your reactants are going to be up here, because they have a lot of energy, and as they release energy, then your products are going to have less. So that's kind of weird. And in this case, that enthalpy, so H's are enthalpy, and THALPY. And for all practical purposes, for this class, as long as you're at constant pressure, enthalpy is heat content. So H is heat. So if you're the delta integral into a triangle in physical science, that means change in. So delta means change in. So literally, if you have a value for what we call delta H, you have a change in enthalpy. And if it is an exothermic reaction, then your enthalpies are going to be negative. You see where delta H less than 0 means it's going to be negative. So that's an exothermic reaction. All right. So another energy diagram, and like I said, what you start out with has more energy. It's going to release energy as it reacts. So what you end up with has less energy. So go from reactants to products. But I kind of like my energy diagrams that kind of, well, I guess it didn't kind of start. That's not what I'm used to. But it does a similar thing. So endo and exothermic, endothermic energy in, exothermic energy out. So endothermic energy in, we can put heat as a reactant. So we put it on the left side. Exothermic energy out, so we can put heat on the right side. So this can be a very practical thing. I've got a couple of things up here to kind of show you. I don't know if you've ever seen these before.
and stuff that they use over there.
I like to.
I'd like to, it's just finding the time to do it nowadays.
Right. Now that your girlfriend has a puppy.
Yeah. Well, we can just take the puppy fishing, but just like work and school and just like trying to keep track of everybody in life and all that socially.
Gotcha. Juggling all those things.
Yeah. That's just it.
That is. So, what this slide says is what we could have done with kind of what you gauged the coldness, how that beaker got cold. We can actually quantitate that, so we can come up with a number for the change in enthalpy. Remember, delta H is change in enthalpy, change in thermal energy. So if it's associated with a reaction, we use these subscripts. I like RXN or delta H reaction. A lot of times for these sort of, we call thermodynamic constants or something to do with energy, they'll be in what's called the standard state. So you'll see that little superscript. So we delta H and we call that a knot, like KNOT, delta H knot. KNOT. And that little superscript 0, it's a knot. And the standard conditions means that your reaction is occurring two things. We got to knock out temperature and pressure. So basically T is equal to 25 degrees Celsius and P is equal to 1 bar pressure, which is about 1 atmosphere. So that's what the little knot means. So heat of a reaction. Very good. So I'm going to kind of I'm going to pick on this chemical reaction where we're making water. Just making water. This is a balanced, because we talked about balancing the equations. You take 1 mole of H2, combine it with 1/2 mole of O2, we're going to get 1 mole of H2O. So it's saying that 241.8 kilojoules of energy are released. So does that make it endothermic or exothermic? Exo, yeah, releasing it. Yeah. If energy in would be endo. Yeah. So this reaction is exothermic. And so we can put heat on the product side. So because it's releasing it. So we could rewrite the chemical equation. The only thing that's different here is I've added plus 241.8 kilojoules of energy. Okay, so I'm just kind of taking it and kind of making a picture. In a minute, actually, this is not how we leave it, like in chemistry and physical science. I'll show you how we do it. This is one way to think about it. So check this out. What if instead of, I bet you can answer this, what if instead of 1 mole of water, 1 mole of water, formation of 1 mole of water will produce this much energy. What about 2 moles of water? Exactly. Isn't that cool? Yeah. So on this slide, if you take this energy, 283.6 kilojoules of energy, it's twice the last one. Makes sense. So what you just did intuitively is the way it is, in that when somebody gives you a heat of a reaction, a delta H RXN, or energy released, it's specific for that particular balanced equation. Because you know we can balance equations, we can scale them up and scale them down, right? So instead of presenting it, that way, what we usually do is we put the reaction, and I put like maybe sometimes a semicolon right here. So the difference between this one and this one is I am simply kind of writing the reaction, and then I'm saying the delta H, and sometimes say delta H RXN, because I like doing that, RXN, is, and notice that a few slides ago we said if it's exothermic, your delta H will be negative, and that's exactly what you're seeing. If it had been endothermic, my delta H would have been positive. So it's negative because it's exothermic. All right. Cool. So in italics, again, the enthalpies of reaction, the delta H, R, X, N, are specific for a balanced equation. So you always have to, they have to give that to you. So just to kind of summarize what we just did, all we did was, if you, our case, we multiplied, we scaled it up times 2, how much H2O we produced. So we had to scale up our delta H, R, X, N by that same factor, which was 2. There's all sorts of kind of neat little chemistry problems that we're not going to get to in this class that you kind of do. It's called Hess's Law. It's kind of fun. So let's kind of, let's take that one step further. So, so what's the relationship between negative 483.6 and negative 967.2? Okay, so this is just times 2. And then actually this is kind of consistent because the amount of water produced is times 2. We could have done it, we could have done any of these. All of these are times 2, Well, what are we going to have to do for that third one then? If we're going to basically take the first one and we're going to go back to forming only 1 mole of H2O. Yeah. Divide by 2. Yeah, exactly. So in this case, if we take negative 483.6, you divide by 2, you're going to get negative 241.8. All right. So what if we flip it around? So we've been building water. What if you take water and break it down? Perfect. You've got a good instinct, Cole.
Yeah, a lot of like math and science really is just kind of like instinct like that.
Yeah, but not everybody can think, but
yeah. Go one way, there's like
right. That's true. And that is totally the case here. So, all right. So yeah, we're taking water, we're breaking it down. So what will be the amount of energy that will be required? What do you think? Related to the amount of energy that was released.
Be the same, just positive.
You're no fun, Cole. Be the same, just positive. Yep. So in the previous case, it was exothermic. So in this case, when we switch around, it's going to be endothermic. You're right. It's going to be positive delta H. Very good. So kind of the rule of thumb is if you have to switch reactants and products around the reaction arrow, yeah, you change the sign of the delta H, just like you said, but the magnitude of the energy released or absorbed will be the same. Okay, so yep, here we go. We're breaking down 2 moles of water instead of forming 2 moles of water. And like I said, if I was doing this in my paper and pencil, I probably would put a semicolon here because I want to distinguish, here's the chemical reaction stop, and then here's the enthalpy of the reaction. And it's positive. Yep. Instead of negative, meaning it's endothermic instead of exothermic. So here's the 2 things that we talked about. They're tools in your toolbox of kind of getting the reaction that you need. What's that?
By sign of delta.
Yeah, yes. By sign, it means positive or negative. Choose the sign. Yep. Okay, so one other thing I want to talk about now is this idea of stoichiometry, using the balanced equation to know quantity of energy that's required to release, okay? And we'll end up we'll be given the heat of the reaction, the delta H RXN, and we're going to make like a ratio that we can use it to knock out a problem. Okay, so this sort of problem I want to do is basically, I think what I said is how much energy will be required to release given an amount of a reactant or product. Okay, so we're going to pick on this one. Is this endo or exothermic? It is endo. Very good. And one of the things I like to do is to take amounts and to put it under what it is and it's something like this. So how much energy is released? So maybe over here, the delta H, I'll put energy equals question mark. And then I'll say, it says 2.35 grams of iron is reacted. So I'll find my iron, and I'll put 2.35 grams under my iron. So to work this problem, we're going to take that mass, and then we're going to go to moles. Take the grams of iron, go to moles of iron. How can we do that?
2.35 grams over 1 times 1 mole of iron over the...
You got it. That was just that's perfect. I'm just going to put molar mass of iron. Perfect. And then we can go from moles of iron to energy, and I'm going to show you, well, I can just do right here. Recognizing that we are going to have 799 kilojoules of energy released for every 2 moles. That's going to be that's going to be the ratio we use. Do you see how I got that? 799 kilojoules of energy released for every 2 moles. I should put Fe, sorry, my bad. 2 moles Fe. My next slide kind of emphasizes that idea of you can take that energy is associated with any of those quantities. So we could say that that energy is the energy released for 2 moles of Fe. That's the one we're going to use. But what if you had moles of Cl2? Then you would do this one. 799 kilojoules of energy released for 3 moles of Cl2. Or you could pick on the product. That amount of energy is released for every 2 moles of FeCl3. So it just depends on what you need to use. Now, one of the things, and I kind of underlined the word released here. So this is a sort of problem where you need to keep, and you will keep your wits about you that it's a negative delta H, no energy is released. Notice I didn't put the negative here. Honestly, sometimes I do put the negative here, just to remind myself that it's exo, and I don't think you can go wrong that way, because then that will introduce a negative sign in your problem. You get a negative energy. Like, oh yeah, it's negative because it's exothermic. So I think you can. So it's not
just like do the problem one way and add the negative sign here because it's exothermic.
Yes. Yeah. Either way, and I think I like to maybe introduce it earlier, just carry it along. So otherwise, I might lose my little release thing. Energy's released, so it has to be negative. So you already told me this. You said we can go from the grams of iron that were given to the moles of iron using the periodic table, molar mass for iron. And now we've talked that we can go from moles of iron to kilojoules of energy using relative energy change, which is just that ratio, energy over 2 moles of Fe. So here we go. Just like you said, the first term, I like to put it over 1 to emphasize I have units of grams in the numerator. And you said I'm going to go with 1 mole of iron over the number that's on the periodic table, which is 55.85 grams of iron. And then what's that last term? Mm-hmm. So what's this last ratio? So this is where we're going to go to energy.
Oh, we just plug in what we were now.
Yep.
So 799 or negative 799 or 2 moles of iron.
Exactly. I probably would put negative. And how many significant figures?
3, because we were released, right?
Yep, 3 at least. Very good. So you should get 16.8 kilojoules. Cool. Ta-da. All right.
Negative 16.
I think so. Or I don't have it on my slide. You could say 16.8 kilojoules of energy are released. Goodness, my pen's kind of going wacko. But I don't know. I don't know. To me, I probably would have a negative there. So then these would be due on Monday. And then Monday, we're going to start on the 5th unit.
We'll try to get the
Okay. I've been at the end of the semester. I'm behind in grading, so that means students can be behind in turning stuff in.